Hello. In this tutorial, we're going to be discussing some more advanced topics about recursion. Specifically, in the last tutorial, you saw how to define a recursive function and how to make use of it. You should remember that a recursive function is defined upon itself. It has a terminating case, and then each time the function runs, there's going to be some work done that moves us closer to that terminating case. What I'd like to talk about now is a means of doing recursion where sometimes the recursion has multiple base cases or kind of ending cases, and also how a recursive function can also call itself more than once. And a good example of this is the Fibonacci function. So the Fibonacci sequence is a set of numbers that looks like this, as I'm writing out. And you'll notice that the first two numbers are 1, and then thereafter the next Fibonacci number is just the summation of the previous two. So I derive 2 because I'm adding 1 and 1, and I get 3 because I'm adding 1 and 2, and I get 5 because I'm adding 2 and 3, and I get 8 because I'm adding 3 and 5. So you can see these progress up quite nicely. Let's write a function that does this for us. We're going to create a public static int. It's going to return an integer value to us, and we're going to call the function Fibonacci, and it takes in n, and it's going to return to us the nth Fibonacci in the sequence. Now our base case here is if n is equal to 0, we're going to return 1. That was that first Fibonacci number. I'll write them again just so you can see them in your head. And so on. Okay, so here's our Fibonacci sequence. So if I'm at 0, where n is 0, I want to return 1. Otherwise, else if n is equal to 1, I want to return 1. Okay, so we've established our base cases now, where we have two base cases. We could also write this as if n is equal to 0 or n is equal to 1. So that would work as well. And we could just kind of reduce this down to one base case because we're returning the same thing. Otherwise, if we're not at our base case, then we want to return, and remember that all paths through our recursive function should return a value since we're looking for an integer to come out. So we have three different possibilities here. And if we're not at a terminating case, then I want to look back. If I wanted to calculate this Fibonacci number, I need to calculate the Fibonacci of n minus 1 and the Fibonacci of n minus 2 and return the summation of that. So normally we would the recursion would call itself, this function would call itself and move closer, maybe by n minus 1, but to calculate the Fibonacci sequence properly, we actually need to recursively call on n minus 1 and recursively call on n minus 2, and then add that result together. Okay, so it's a pretty simple function to define, but the important thing here is that we have multiple base cases, and also the function is calling itself more than once. Let's go up here in main and make use of this Fibonacci function we just wrote. Let's say we want to calculate the first 10 Fibonacci numbers. We could do Fibonacci of I. We'll go ahead and do system out println then. And so we're just going to loop across the first 10 Fibonacci numbers and print them out to the screen. And if we run this, you'll see that we get 1, 1, 2, 3, 5, 8, 13, 21, 34, and 55, just like we had defined the function. So it looks like it's working properly. If we want to increase this, we can get more of the numbers. Let's say print the first 20 numbers. And you can see that where we left off with 55, it just keeps going, and we have our first 20 Fibonacci numbers. Well, as a comparison, let's talk about how we can implement this iteratively here. I'm going to create a new iterative Fibonacci function that takes in an integer as well and returns to me an integer. And the work I'm going to do this time is just to calculate this, and rather than recursively, I'm going to calculate it using iteration. So I'm going to use a for loop here, starting off I at 0, and so long as I is less than n, I'm going to repeatedly move the numbers that I'm looking at up by 1 and recalculate. So the way this is going to work is I need two variables a and b, which I'll initialize to 0 and 1, and I'll need this temporary variable because I'm going to do some swapping about here. So temp, every time through the loop, I'm going to essentially take the two numbers that I have and recalculate a third, and then shift the two numbers that I'm looking at up. So I always have a window of two numbers that I'm examining here. So we'll say that temp is a plus b. I'm calculating the new highest Fibonacci number in my sequence. I'm going to shift b down, and then I'm going to set b to this new number that I just calculated. Now I do need the temporary variable because I can't do the recalculation without wiping out what was already there. Okay, and that's all that's to it. And then I'll just return b. So I set up my initial variables. Notice if n was 0, then I'm never going to run this for loop and I'll just return 1. If n is 1, then it's going to add 0 and 1 and move b to be 1, which is the new calculated sum, and then I'll drop out of my loop. If n is 2, I'm going to go through this twice, and I'll eventually add up 1 and 1 and return 2. So let's test out this iterative Fibonacci. Rather than calling Fibonacci in my main function, I'll call iterative Fibonacci. And let's run this. And we get the exact same sequence, 1, 1, 2, 3, 5, 8, 13, 21, 34, and so on down. It's 67, 65, and if you want to, you can rerun the Fibonacci and verify that 67, 65 is the 20th Fibonacci number in our sequence. So here's a nice way of comparing and showing that if I can do it recursively, I can do it iteratively, and vice versa. Sometimes it's easier to express our function recursively. In this case, the iterative solution is pretty easy, but sometimes different data structures might lend themselves to recursion over iteration. So always realize that recursion and iteration are two different sides of the same coin. It's just a way of getting repetition. In this tutorial specifically, we focused on how we can take a recursive function and have it call itself more than once, or have different base cases, more than one base case. And at this point you should be asking yourself, okay, so if they're the same, then why do I care? And understand that sometimes data structures and what you're trying to do might be easier to express recursively like we did here. The trouble with recursion is that it does build up that activation stack, and so from the previous tutorial you saw that every time I call a function it adds to this activation stack over here. The other problem is, if you look at mathematically, we're doing a ton of work here. That if I wanted to calculate the 20th Fibonacci number, I need to calculate the 19th Fibonacci number and calculate the 18th Fibonacci number. But in calculating the 19th Fibonacci number, I have to calculate the 18th and the 17th. And to calculate the 18th, I need to calculate the 17th and the 16th. So we're actually doing exponential work here to do this. Whereas the iterative Fibonacci function is linear, and if I want the 30th Fibonacci number, it's just going to go through this loop 30 times. Up here, if I wanted the 30th Fibonacci number using this recursion, it's going to do an exponentially large amount of work. It'll have to calculate Fibonacci of 29 and 28, and it just grows like mad. Tons of work that we're going to have to do. To drive that point home, I don't want to calculate the 20th Fibonacci number because that actually runs pretty fast, right? We can run this in 0 seconds, and it goes pretty quick. Let's grow this to 30, and I want to calculate the first 30 Fibonacci numbers. And this takes 1 second, still not bad. Let's grow this to 35 and see how long it takes. Now it's taking a little bit more time. What if I wanted to do it to 40? Now you can see it's taking us a little bit longer. There was a bit of a pause there in those last few numbers, and it took 2 seconds. And if I do to 45, the first numbers are generated very, very quickly, but then you can see that it's slowing down the larger the number, the more work I'm having to do, and it takes an exponential amount of work to get the next Fibonacci number. So it takes really kind of twice the amount of work. Every time I add a new Fibonacci number into my main loop here, it's going to double. So that one took about 20 seconds to complete just to get the 45th. Now watch what happens when I go to the 46th Fibonacci number. It should take 20 seconds plus about another 20 seconds to do that work. So we'll sit here and watch this go up, and as it's doing the calculations, I'll point out to you that sometimes performance is very important, and for very small problems that you're solving, the computer might solve it very, very quickly, but you need to consider what happens when you have a large data set or a large number that you're trying to work with, and how does your algorithm and how does your code handle that. So notice we went from 20 to 32 seconds. It really adds quite a bit of work just to add one more number here. Now let's leave it at 46, which took 32 seconds in the recursive version, and watch what happens when I use the iterative version instead. We're going to run this, and it's going to calculate in 1 second rather than 32 seconds. So we had a huge performance gain by just going and using the iterative version over the recursive version. Now I don't want to leave you with the impression that recursion is bad. It's just, depending on how it's coded, it could be costly in how many calculations you're performing. So realize that recursion is a powerful tool to express a solution, but it can be performance costly if you don't approach it properly and solve the problem in an intelligent way. Okay, so this tutorial should have showed you how we've got multiple base cases that we can define in our recursive functions, as well as we can call a function recursively more than once, but realize that there's a cost to pay for that, and that we're doing an exponential amount of work here. So sometimes the iterative solution is actually, from a performance perspective, much better. The clarity aspect of this, yes, this is functional and it works and it's much faster, but it's probably not as easy to express and understand mathematically what's going on. And that'll do it for this tutorial on a little bit more advanced recursion.